Try again. Okay, so so remember that we did as an introduction to we did the one I know the two input one and then okay, so elimination theory as much as you can. But they're very different things. So a function of two variables is pretty much a terrain. Visualize the easiest way to think of it as the terrain. On the other hand, the parametric curve is the easiest to think about as a motion on the plane. In there, so even though we will start to these the simpler one. So one step up from one in one calculus, most of the calculus, and then yet we make it one more step, and then 2 plus 2. Okay, so that's what we are taking is 2 plus 2, meaning that 2 inputs, 2 outputs. And so what is the interpretation of that? And one that I suggest already, it is a flow on the plane. So ever like on the plane where that liquid is flowing. Okay. So then 2 inputs, a point on the plane, and the vector points the direction. Okay, so 2 and 2. Okay, that's where it comes from. But we're gonna nonetheless, that's how you would introduce it most likely, and it is very tangible. But our interest in linear algebra in a more kind of a less calculus sense, and that once again 2 plus 2 right here, but with from the where we started with. Remember that was the mixture problem. Okay, so mixture problem, and then turns out yes, we were able to interpret it as 2 plus 2 problem. 2 inputs, naturally you can guess already that's x and y, and then secondly you have 2 outputs for the other 2 outputs. Those two outputs in total. Okay, so 2, so the prices are set up. Okay, prices and those 4 coefficients are set up, and then the 2 inputs are x and y, the weights of the 2 types of coffee, and the outputs are the two requirements. Okay, right here. In this particular case, for our particular problem, 6 and 14 are required outputs, and that creates a function of 2 inputs, 2 outputs, 2 plus 2. Okay, so once again, we don't want to think about it as a vector field as we call it in calculus, but right, because it takes in the wrong direction, but rather this a function with 2 inputs, 2 outputs. Okay, so which is also can be seen as nothing but a combination of 2 functions of 2 variables. Okay, so one and the other one. So for each of these 2 equations that we started on the first day of class, we started with those 2 equations. They actually represent 2 functions of the variables. X plus y, one function of the variables x and y, the other one 2x plus y, 2x plus 3y. Naturally, if we were to keep them separately, we would visualize them as linear surfaces would be planes. Okay, so 2 planes, but into an intersection and like that. These are 2 points. Together to one single point. So we know that that it's good idea to combine them together into one point. But now the outputs too. It is once again, it's not a new idea. It is the idea of parametric curves. When the 2 outputs, you can watch separately, x-axis and y, rather the 2 directions of your motion separately, or you combine them together in a point, and then that's it turns out to be very productive. So now we're doing the same things. And so what's the best interpretation of this? As a matter of fact, and the best interpretation of this, beyond this problem, we're getting to that, is a transformation of the plane. So x and y is a point on one plane, and there's the other plane, uv, and that point xy somehow thrown into that uv plane. So if you do it with all x and y's together, that plane has been transformed. Okay, so it could be certainly a piece of paper, or more likely a rubber sheet. Okay, so that's the idea that we already explored a little bit. We're starting in that direction again. Okay, so let's once again review these functions. So two functions, each numerical function is a number, and the data is collected in the form of two tables. Same, head, column, and head, and row, x and y, and then they produce different arrays of numbers. Okay, so that's what we see here. So you can do it by hand. You can put them in a spreadsheet. Okay, and so once again, the each x horizontal, y vertical, or vice versa, x horizontal, y vertical, it will produce automatically, looks up according to these formulas right there. Remember what R2C stands for. It stands for second row, same column. So if I'm looking at the yellow spot and I need to compute what's the value to put there, I go R2C means second row, same column. So I'm going up. Okay, so let me try to use a pen actually. I could. So, okay. Okay, so this one goes up, and the other one goes, horizontally. It goes it goes both. It goes C2 goes into the two respective x and y. So one goes up, the other one to the left. The same formula it applies. The similar idea, but the different formula applies to the second. Where is it? I lost already. The second. Okay, just threw me in a totally different place. Oh, here it is. Okay, so two formulas, different formulas, because they're two different outputs. One total weight, one total price, and so they compute differently, but the idea is the same. So you go to x and y in the vertical horizontal direction from the yellow spot where you're trying to put a number there. How do you do it? You go as a reference, find x and y, combine them together in these two simple formulas and produce the number. Okay, so the total weight, for example, if you look carefully here, 6.0, because it is the sum of 6, 4, and 2. Okay, so that's your computation here. Okay, so and here it is there, the formula more complicated. How did I get this 14? I got it from 4 and 2 again, but this time the formula is right there on the right one. Okay, so that's the whole computation, and then naturally, if it is data, it is just you can combine a number of ways. It may make no difference. And matter of convenience for your computational purposes. But if we try to understand actually what's going on, we start looking at we recognize start looking at geometry, and we recognize in the tables we recognize those straight lines. Remember, so once again for the first day of classes, and what if the output is equal to exactly 4? Okay, if it is equal to exactly 4, we can go through the first table and find all of these 4s and mark them with yellow. And that's the total weight. The total price is supposed to be 14. So once again, I go through the table, the second table over here, and mark with yellow the 14s. Okay, so that's we are still in the same exact place. And then we could have proceeded in the same fashion as before and find the intersection of these two lines that we did on the first day of classes. So what's the difference now? This is the difference now. We combine x and y into xy. We combine u and v into v, uv. Xy already have been combined. It is uv taking these two tables, and that's a bit of a challenge. Take two arrays of numbers. How do you combine them? You could certainly try to combine them like this, but that's not revealing that a two-story building. Okay, maybe, but it is more productive to think about the output also as a point, but this time on the uv plane. Okay, so this is the computation. Those two tables that we just saw. Now they are combined together into one on the right. So the the inputs are pairs. Okay, you can see, can you see the pairs here on the left? The inputs are pairs x, y, and then combination x, y. So over there, two and what is it? Two and 5 are combined into 2, 5. Well, wait a minute, it's not it. Okay, no, the inputs are here, but the output, and then we're filling our table with outputs. Yeah, I'm not sure what that's in yellow. In yellow is the double output. Yeah. But that's how the computation is carried out. It is x and y combined together. Two computations carried out and combined into a y point uv. So in which case, for example, if we take once again 4 and 2, let me confirm that works out. If I go with 4 and I go with 2, okay. So as you can see, 614. That's the same 614. The requirement. Remember, the requirement was 6 total weight and 14 total cost. And indeed, that's the table that contains the whole story here. Okay, except we do not set our mind to be 1614 necessarily. We want to solve the problem for every possible mixture of the kind of a blend of coffee that we want to come up with. And so these both the functions are computed at the same time in the same place. So x and y are here. UVs are these pairs. Okay, UVs are pairs, and every combination you can stick your figure anywhere you want. And for example, I can have 11.5 pounds of blend for the price of 5 for $29 price. Okay, so anything I can produce with these costs that presumably are given and not to be changed. Then this computation is carried out. Okay, so that's on the right is just an explanation of how that computation is carried out. The inputs are these on the columns and the rows, and the outputs are those. These are the outputs. So the table is the table of outputs. The columns, the main column and main row, these are the inputs, and the outputs are inside. Okay, so once again, it's just a matter of combining together, computing the number and then combining them together. So once we're there, we are now we're thinking in the more abstract way. We have a plane, xy plane, and a u v plane, and the points go from left to right. And once again, if you know where every point goes, then you know what has happened to the plane, and we already have had a bunch of examples. Maybe not quite enough, but this is how we can write it. Okay, this is how we can write it. Once again, xy is the input, uv the output, and there is a specific formula. It is very, very simple formula that should remind you of the of calculus 1. Once again, I mean, once the formula is there, you can figure out what it does. It's all the explanations are really just a build up. That's the whole story. The whole problem that we're trying to solve is here. And once again, it is a solution not of one original problem when we had a specific choice for total weight and total price, but rather all possible blends are here. So we can go directly. Okay, from x to y, if we know the weight for x and y, we'll have both the total weight, x plus y, and the total price, 2x plus 3y. Okay, and then we are keeping in mind that we might go the other way. Okay, that's where we got last time, backwards. Okay, so we know the outputs we want to go backwards. That's literally called the inverse problem. Right, so there's the direct problem when you plug in x and y to find out what kind of blend you end up with, or you go backwards from 614. Desired outcome. Remember, the other desired outcome came up quite a bit ago when, for example, if it is the mixture about your diet. Okay, so once again, if this is what you have eaten on that day, it will tell you at the end through this simple computation is how much calories or carbs or whatever or fat so you have taken. But also, if quite just as the natural problem is to ask what if this is how much my diet is supposed to be, what combinations how can I produce this from combinations of the foods that I might be. Okay, so backward problem. This is simpler. There are only 2 inputs to outputs, so that's fairly straightforward. So once again, we're looking for the direction to reverse the arrows. It is literally the inverse function. Remember, we reviewed it for a purpose. Not once again what inverses you think of when you do the in pre-calculus. You just solve for x or y. because the algebra is so straightforward, probably. But that's not going to happen anymore, because as you can see, where is the problem? This is the setup of my problem. So the inverse problem, what would it look like? It would be express xy in terms of uv. Okay, so it's not impossible, right? So naturally, remember, if probably you would be make a reference to this, right? So that to make your life easier, split it up and abandon the Cartesian system, forget about geometry, and just look at these two equations. You just have it's just a system of two equations with two unknowns, but now it's not x and y that are known; they actually assumed to be known. It's u and v that, hold on a second, x and y are unknown, and u and v are assumed to be known, and then you just solve for x and y. It's an algebraic exercise, not a lot of problem here. It is just, why do we do it this way? Because it's a simple example, and we still can visualize things, and so but once we go to dimension 3, 4, or higher, all the algebra is out of the window, the visualization is also out of the window, and so it has to be actually done by one and only one way. The computer will have to do it for you. Okay, so beyond anything else, you don't want to do it by hand anymore. So we want to learn how the whole thing operates before we actually attack it in some kind of a computationally feasible way. And well, not in this course, frankly, but at least we'll set up the foundation for it. Okay, so once again, the point, so the solution is not known to be every time you want to assume that there's one and only one answer. Not the case. As once again, to remind you, the first week of classes, it's possible there is no answer in the first place if your prices are just right aligned with your weights. Okay, so this is the price of one type of coffee is equal to the other one, in which case the two lines happen to be parallel, and there is no solution. Okay, in other case, you can have infinite many solutions because they are just so aligned, and every point on this line is a solution. So it's all possible. And once again, remember where it comes from. It is one single point, we're trying to find one single point where it came from. And the answer could be 1 point for 2, and that's the original problem. But also, these are also possibly just change the problem slightly. It's still a linear problem, still a mixture problem, and yet you end up with totally different answers. And these are the three classifications that we're gonna remember, is that it's always one solution, zero solution, intermediate solutions. Okay, so these are the only three possibilities for every problem in linear algebra. Okay, so once again, so this is as you can see, it's not made up. You can just go through the table and see the answers for all. And the answer why is, how can we predict that this is the case? That's how, because u and v, and once again, the price of the Kenyan coffee is the same as the one of Colombian coffee, and in which case, how can we predict without plotting anything that it's going to be the infinite many solutions? The answer is right here. The u and v are actually proportional to each other. V is equal to 2u. Okay, in which case you're looking for, on the UV plane. Now we move to UV plane, and we're looking for the image of our function, basically. And the answer is, it will be a straight line. Okay, one straight line. Rather than, once again, we're thinking about transformations, and we can transform the plane into the plane. We can rotate it, shift, stretch, and so on, still to be discussed. But on an extreme end, what can happen, you can shrink your whole plane into a string. Okay, it is possible. There is nothing stopping you from doing exactly that, even though it sounds extreme. But yeah, you take the infinite plane and string, put it in the form of the infinite large plane, and put it in the form of a string. Okay, so that's what can happen, which means that not every plane is covered, so its function is not onto. Remember, so and that creates the possibility that there is no answer whatsoever. So that's what we ended up with. Okay, so what is this? So once again, remember that idea we talked about transformations a little bit before the test. That was non-specific, but here, and what we're supposed to do is to understand our transformation. Once again, this is where's this is explicit formula, so we're not thinking in the abstract just yet. So so remember transformation of the plane to the plane, and then what is that we have to pay attention to? The answer is where the x's go. Okay, where the x's go, and this is this example. It's all in our hands, right? So the formula is explicit. So look, what if x is not, what is the x-axis? It's y equal to 0. So if y is equal to 0, okay, where do the points go? Okay, so once again, you can certainly see it there. What is x plus y, 2x plus 3y. That's my formula. Okay, so now I'm looking at the red on the x-axis. Y is equal to 0, so I end up with x 2x, right? So if y is equal to 0, I end up with x 2x, which happens to be what is it? It's, incidentally, it's a parametric curve of x. Okay, and then it is a straight line with a slope of 2, but literally it's a parametric curve. So 1 unit to the right, 2 units up. That's what that line is. Okay, so that's you know where the x-axis goes. And then secondly, what if now x is equal to 0? We're looking at the y-axis, and I end up with y 3y. Okay, so once again, it's a parametric curve. And everything is linear algebra ends up to be a straight line, so it is a straight line, the green straight line. So that's what happens to the two axes. As you can see there elsewhere, and there is some kind of rotation as well as possibly stretching and shrinking. And well, definitely stretching and shrinking is visible if you look at those dots. The dots actually come from here, so they were 1 unit at a time, and then they end up on the x-axis on the UV plane. They end up stretched out somewhat. Okay, so that's there is a rotation, there is stretching, there is a rotation of at least of the axis, but there is no flip. Okay, so the how do I know that there's no flip? How would you know that there were a flip?
Negative.
Negative what?
X for y.
Well, you're looking at the formula, surely, and that's certainly might answer you, tell you what has happened. But based on the picture, why there is no flip? What? Both spots. So how would you tell? How would you tell if there were a flip? What would be what picture would it look like? They would?
To be intersecting.
No, they are intersecting. The way they intersect each other. Okay, so imagine just take the picture, take the last picture and flip it. Say upside down. Can you see what if I flip the last picture? I might end up with something like this. So the red one is going. Okay, so I'm flipping. Okay, so that's I took the last picture and flipped it. Okay, so now can you see what? Look at the relation between the two axes, not separately one at a time. What's the relation between the two axes after the transformation? My flip. Yeah, I messed up my flip. Flip goes like this and like that. Okay, so rotation from first to the second. Okay, you see the difference? The original rotated on the original XY plane, rotate from the x-axis to the y-axis in the counterclockwise direction. First, second, like this. Then, if with no flip, that remains the case. The top right picture, still rotation counterclockwise direction. If you take the flip, what is the flip? It's a mirror image. what mirror image does, everything what we used to be left becomes right. And so rotation that used to be clockwise, counterclockwise, that becomes clockwise. So that's the difference. Okay, so it is a quite a reversal, literally a reversal of things, when the relation between the two axes has been changed to the opposite. Okay, and so once again, it's not the left and right as much as the direction of the rotation, clockwise or counterclockwise. Okay, so it is literally what I suppose. How do you notice that? Yeah, so look at the clock in the mirror. It is going in the wrong direction. Okay, so we'll talk about that, and there is a way to find out. That's part of our further development. Is there's a way to find out when from the formula when there is or there is no flip. Okay, it's called change of orientation. It's a your piece of paper this way or that way. So it's a big deal, but from the when there is no picture, you still should be able to tell whether this is the case or not. Okay, so that's our formula again. Solve for the independent variable. We only can do it using the like middle school algebra. We can solve for x and y separately like this, and that's the solution. I don't want to go through it, but it's pretty much a triviality, right? So y is equal to u minus x. So you solve for y, substitute to the second, simplify, end up with an equation that involves only x. You have x that solves half of the problem. Substitute back into y, and you have a function for y as well. So these two answers, the two solutions that we now have produced through this, once again, nothing but middle school algebra. And then this is but we then recombine them together into a function of two variables, a transformation of the plane. But this one works backwards. UV is the input, and xy, what's on the right, is the output. We're moving backwards. As you can see, there's a u and v, all of these are present, x, and then a bunch of minus signs, by the way, it's also present, does not indicate on its own whether there is or there is no flip. Okay, so the flip is not so easy to determine, but it's possible. Okay, so the problem is solved. Okay, so in a satisfying way, which is satisfying, meaning that this ideas that you have put forward. Now, not the algebra. So this algebra is not reusable in higher dimensions. Okay, but the idea, the rest of the ideas are, and that is, well, what are those? Points are numbers combined into points, depending on the number depending on the number of numbers. So 2 it make you a point on the plane, 3 in space, 4 in 4-dimensional space, and so on. So there is no stopping there, and so visualization is out. But if we at least have a picture in our mind, something like that, it helps in high dimension too. The algebra itself that we do right here does not, but the idea is still there. So we have a transformation of possibly high dimensional space into another high dimensional space. And what can happen is in linear algebra, nothing much there, but a combination of these things that we have already seen, and those are stretching, rotations, and possibly flips. Okay, so all of that will remain a fair game in high dimensions. Okay, but otherwise that's what it is. So then we kind of pause here, in the sense that so high dimensions, just to start thinking about them. We're still in the two-dimensional space. Everything is fine, but once again, even 2 and 2 already form. Okay, so we already in trouble. So we are twisting our minds in order to try to understand what's happening when there are total of four variables, and we kind of figure it out more or less. Okay, so that's not the end of our study of two-dimensional space. There is also that's algebra. We do purely notice there have been no measuring. There have been no measuring whatsoever. It's pure algebra. I could, this picture shows, I can stretch the v-axis horizontal, vertical. It makes no difference whatsoever. There are no units involved here, because x and y, it's just how many, and there is no. So it's something that you notice in calculus, that measuring it actually is crucial in calculus. But for now, it has not been used at all. So measuring how close the things are, it's a foundation of calculus. Remember, you cannot have limits without measuring distances. And you can say that getting closer and closer to this number, or this approximates that. Once again, it's how close we are one to the other. So anyway, so once again, for the sake of calculus in part, but also for to develop the multidimensional spaces in full, and which means that not only algebra, which we're starting to understand now, but also geometry, and those will be measuring starting with geometry and measuring. That's what it means. Measuring things such as distances to begin with. So Cartesian system. Let's quickly review the Cartesian system of the plane. Once again, I'm making a distinction here between what we have been doing, and especially in calculus 1 comes out a lot. The Cartesian plane is used to plot functions. Okay, x is the one variable, y is the other variable. There might be no relation whatsoever between them. Therefore, in the middle, top middle, I take my xy plane, I stretch it horizontally. It makes no difference. And Excel does that too. You have a table, you have a data, and then you click insert chart, and then you can resize the window anytime you want. That's a normal data and the normal state of affairs in calculus, pre-calculus, and so on. When we are talking about functions, and so once you start changing shapes of the xy plane, then there is no difference between the slopes are changing. Okay. The ones that you see in the circles and ellipses are the same too. So that's certainly not where we are right now, because remember the why didn't we care about that about the why did we allow the stretching? Because the inputs and outputs are unrelated to each other. If, on the other hand, we are in the same place as we are right now, remember xy plane is actually these are the weights. X and y are the weights, and probably used in the same units. So which means that being related to each other and they together form the domain, we better treat them differently. We treat them as equals, and therefore the units should be the same. Therefore, we have to have squares. We are not satisfied with rectangles. We are not allowed to stretch our space just arbitrarily as you would do in Excel. So then the geometry that we were to study hypothetically, or we did in high school geometry, triangles, circles, parabolas, hyperbolas, whatever. They are not just cannot be stretched out without consequences. The distances change, and so then what's in the middle is what we prefer now is as I said, square, not just rectangular system, but squarely system of coordinates. X and Y's have you have the same units, and then we can do geometry that used to be on the plane. Now on the piece of paper, now we can do what we call analytic geometry and do measurements in terms of the coordinates. Okay. So the geometry on the right, that's the how you transition from a Euclidean plane to coordinate plane, and then you place the like a transparent piece of plastic with a grid on it. You can place it this way, that way, that makes no difference. And then you start measuring things. You represent the figures in terms of formulas usually, and then those formulas can be plotted, express this function, and so on. That's how happened before. Right now, just our idea is to do very simple things. Do measurements in terms of coordinates on the plane that has equal units of horizontal and vertical. Okay, so analytic geometry, and so we can then measure primarily two things for now: distances, but without a ruler or measuring tape. There are two coordinates of the points, and then four numbers, and from those four numbers, you're supposed to find the two. What is it called? The two points, two coordinates each. I combine them together and find the distance. What's called? No. Well, so coordinates are here. Okay, four numbers I combine together to find the distance. help you out with about this. Does this help? It is, yes. Ultimately, it is the Pythagorean theorem, although the name that I was trying to maybe remember is called the distance formula, but it is kind of where it comes from, the Pythagorean theorem, and that's why we want to have the Cartesian system to be rectangular, so we can easily apply the Pythagorean theorem as needed. So, and then the angles, secondly, the angles later on. But so we start with distances, and in fact, to keep things simple, let's start from scratch. Once again, we are as if we're doing the same thing. We did algebra for dimension 1, then dimension 2. Now we're doing the same for geometry, dimension 1. And so how do we measure distances on the road? And the answer without measuring. Okay, so people are just as long as you know where you are, which might be indicated by, say, milestones, you should be able to find out how far you are from a particular location. So if you are at milestones 3 and the city is at milestone 5, then you know that you have to cover 2 miles, right? So that's how. So in dimension 1, things are way simpler, but we start with them because remember, just like algebra is made of two axes to produce the plane, same story happens with geometry. So milestones, and then that's the construction there, how you can create the real number system to remind you with the dimensions. So a line, then step 2, you choose the positive direction, choose the 0, put the O there, then choose the unit. And use the unit to the left or the right to place infinitely many milestone on that road, and then the end result is a line, and then that line is now creates that simplest coordinate system when there's only one number, but it works perfectly well. So it's just the coordinate system has been used for to travel through sea over seas and on for dimension 2, and if you go to space, then you need 3 dimensions. But they started here. It started here, milestones on the road. I'm not sure. Maybe I can't remember. So Roman roads, if they have milestones, they must have had it. So that probably was the original place for the first time coordinate systems were used. And then the something to worry about. Let's make it slightly more complicated, and that probably doesn't come up a lot, and that is 2 different unit systems. Okay, so you can do kilometers or miles, and then in which case you supposed to have it's the same road but different markings. So you're supposed to translate from one to the other, and so for example, in this case, you coordinate 1.5. So I have a two very simple systems. One goes 1 at a time. The other one is well, actually, as you can see, there are 2 differences. One difference is the units are smaller for the second one, U. Firstly, and secondly, it starts in different place. So 0 is located in different place, which means that you have to be able to translate your coordinate in the first axis to the coordinate of the second axis. Okay, so in other words, if I know the coordinate in x, one number, okay, so I need to find the coordinate of y of u location, let's say number p, which is on the one hand is 1.5, on the other hand it is 2, and I should be able to should have a formula that gives me u for each x. You see what that formula is? You surely could try to guess it. If without guessing, how would you go about finding that formula? What kind of formula is it anyway? 99% of the time in the course called linear algebra, the answer will be linear. So in other words, u is equal to mx plus b. Okay, so which means that you need to find these 2 numbers. Okay, you can guess what m is for sure because it is what's the meaning of m. It's the slope. Yes, if you start plotting it. We're not plotting it. So it would be the case if I put x and u like this, then on that plane m with the slope. And here it is, what is it in this context, in this picture? What's the meaning of m? the change of unit, right? So the units of x is twice as large as the unit of u, which means that if I want to find how many units there are, what do I do? M is equal to what? It will be 2, right? It will be 2. So for each unit on the x-axis, there will be 2 on the u-axis. So then what remains is just b. What's b? The meaning of, if you remember that, once again, if you go back to linear algebra pre-calculus, b is the one-intercept, so you can go to 0 and find out what it is, or you can just look at this thing. So when x is equal to 0, when x is equal to 0, u is equal to -1. So v is equal to -4. So and then so did I do it right here? So I did the other way. So but so the two are 2x minus 1 indeed, and then there are 2 are incidentally inversions of each other. Okay, so that's the conversion, and you realize that that's might seem too simple, even though you probably have never solved that problem before. But it's crucial once you start studying the space with no specific 0, that there is no origin. So I don't know what they say, the sun is in the middle of the universe. That's simply not true, right? I don't know what Copernicus says. And then, so there's no 0, and the units are also, they're not set in stone. So I go kilometers, even though they say the metric system is the best, I also don't care. There you can change the system, and once again, everything correct. And then thirdly, so stretch, that's a shift. If you move your center of the universe from the Earth to the sun, you shift. And then secondly, you can change the units from kilometers to miles or whatever. And thirdly, you can rotate too. So all of these things will produce this different coordinate system for the same universe. Okay, to begin with. But the idea starts here in the one-dimensional case. So we'll deal with that later once we get to it. For now, this is how we can change. So in this particular, you have some kind of a formula, and then you can transform the formula into the new one. So that's how compositions come into play, and that is change of units requires you to substitute your change of units. That formula that we just discovered will be substituted into whatever functions you have had. So you have Newton's laws, for example, written for one coordinate system, and then you're supposed to rewrite them for a new system. Okay, using these formulas. So, and that was the big deal of when they started to examine different coordinate systems, including the ones that may be moving in space, and which means that that's how, in many ways, the relativity theory came about. So, what's the effect of changing of units, or change of variables, change of a reference point to change of coordinate system? What does it do to the physics? And there should be no difference, right? And then sometimes you might discover that there is, and then you start thinking about it. Anyway, geometry and algebra, we go back and forth. Coordinate system will give you the nothing but a pair of numbers, and those pairs of numbers can produce the location. So that's the two-dimensional case. It works the same way. It works the same way between, as you superimpose the coordinate system on the top of the geometry that we know that our outside of our control. So we put that piece of plastic on top of it so that we could control it, and we replace this geometry with algebra. Okay, so that's the idea, and what remains is just to be clear about what it means, that now coordinates correspond to points and points correspond to coordinates. In what way? In the same way, we just as we understand how we put milestones on the road and understand the correspondence between your location and that milestone, the number that you see. Similarly, you can think about when you have a plane, you have a grid. Okay, instead of a line, you have a grid, and you can think about streets, street grid, and then you indicate your location within the grid by saying what number street, 3rd Street, 5th Avenue, stuff, intersection. That's how you know two numbers tell you your location. Okay. The build is like this. So once again, we have two identical this time. So you might remember we did the XY plane once before, but we did not require the two axes to be identical. Now they are, because they have the same units for horizontal and vertical. We also require 90 degrees for the sake of Pythagoras. And that's the system on the right. That's our grid where everything will be happening. So once again, translated into algebra. Okay, so all right, so that's the description. Sometimes just a warning that sometimes the that grid that we superimpose on top of the nature around us, sometimes there's no match. So if an airplane measured distance is measured in miles, but the elevation is measured in feet. Okay, so it can happen, which means that, what does that mean? It means that the Pythagorean theorem simply is not very useful here. So yeah, unless you translate it backward. But they don't care because the difference is so huge in comparison. Horizontal distance way bigger than the vertical, so they never care about it. They are 50 miles away, means that it doesn't matter what the elevation is. Just as well, you name both elevation and distance separately. You have two numbers. Okay, two numbers. Once again, the different system. Once again, this is what we just saw a minute ago. What if I change the grid? I make a bigger grid. So a very simple exchange, and you can see how I simply enlarge every rectangle by 2. And so the transformation, then the change of variables, change of units, or the change of coordinate system, that's the proper way to put it. The change of coordinate system is once again is written by means of a formula. So I have UVs on the right, I have XY on the left, and once again, I should be able to express UV in terms of X and Y. X and Y here. So you see what's the formula? Well, you can ask yourself separately. So here the formula is supposed to have two points, but you can write U is equal to something and V is equal to something. And once again, what kind of formula? U is expressed in terms of X and Y. What kind of formula is it? 99% of the time, the formula, the answer is linear. Okay, so U expressed in terms of X and Y. Look at this one. So if I take this point, for example, 1. So the same location used to have coordinate 2, 0, and now it has coordinate 1, 0. So what has happened? That's the same point. Well, once again, it's not just separate axes or coordinate systems. It's the same point. They overlap the same nature as a piece of paper with things drawn, and we just decided that plastic on top of it would look different. So these are the same points. So 2, 0 here and 1, 0 there is the same point, two different coordinate systems. So what do you do to get 1, 0 from 2, 0?
U equals X over 2.
Yes. Okay. So because there is no Y, by the way, which is a really simple transformation in comparison to what we just saw earlier today, when there's a U and a V, and the X is rotate. There is no rotation here, right? So U stays U, so X becomes U and Y becomes V. Okay, so but they do it in an identical fashion. So you just either way you should divide by 2. So that's how you find. So if you know the coordinates of X and Y, then you find the coordinates of U and V of the same point, and that's your transformation. And whenever you go backwards, you multiply by 2. So that's the whole story here. Okay, so once again, whatever curve you have already drawn in the original curve, in the original coordinate system, you can redraw it in the recast it in the new one, just doing the substitution. So if this was my formula, x squared plus 2y, then the temperature depends on the location. For example, I just replace x with 2u and y with 2v, and that's my new formula. So as you can see, that's kind of, it is a transformation, very simple transformation. It is in fact how would we describe it? It is, even though I say it is, yeah, it is, I guess he says it's a stretch, a uniform stretch. So in other words, a uniform meaning that in all directions it goes the same way, so the shapes do not change. Squares remain squares, circles remain circles. And then, so it's a crucial step for us to know if we were switching to different locations. Shift in another possibility. So in this case, at the bottom, so shifts, that's x plus 3, shift in the horizontal direction, and then y line equal -4. It's down in the vertical direction. So there you go. So that's another one. Changing of the reference point, change of the units, change of the reference point. These are the two main things that you encounter. Rotation is more complicated, but so we'll deal with that later. So that's also can happen. But this is how we write transformations. Once again, just an example, a couple of examples of important transformations of the plane, a linear transformation, because the change of units is multiplication, it's linear. A change of reference point, you move to 0, it's a shift. So once again, linear rotation, it's also linear transformation. As you can see, why do we know it's linear? The distances do not change. It is actually the plane remains intact. It just orientation changes in space. And once again, it's all about the compositions. So x from xy to t, that's something you have had already, suppose. And then you want to change the coordinate system to the new one. What do? You just you have a change of variable, change of coordinate system formula, number one, and then you just do a composition of these two, and then you have a new formula. Yes. Okay. So once again, coordinate system, bunch of them, same plane, same pictures that exist, and then we express them in different coordinate system. The result, naturally, when we go back, the result should be the same. Okay, so otherwise, what's the point? Shift. So to remind you, the three transformations that we saw: linear transformation of the line, the shift here, the simplest one. It creates a new coordinate system, and so that's for us to worry about. But I think I'll skip this part. So I'm flipping the idea here. We just showed that if we have a new each transformation, or rather each change of coordinate system, is implemented by means of a transformation. Conversely, every transformation is, it can be seen as a change of variable. So that's a change of coordinate system. So here it is. So just coordinate system is elsewhere. These are the formulas. We have seen them before, but now that once again, that transformation can be seen as a change of units. Okay, so this is the, remember the so the 6, the shift, stretch, and flip in the along x and y axis separately gives you 6, and beyond that is already we saw. This is the example, and that is the flip about the diagonal. Okay, so it cannot be represented as in terms of the other two. Okay, because those two, if you're doing only operation with respect to the x-axis, then that forever remains the case. But this one is a new operation, and in addition to it is the rotation. Okay, so the rotation, these are infinitely many rotations right away, also for us to figure out. This is also not quite obvious. This is another linear transformation. Okay, so it's a skewing of the plane. So in addition to what we have had, this is what might happen. So as you can see, there is no stretching in the vertical direction. It is literally skewing. So as you can see, what happens is a square becomes a parallelogram. Okay, so have you seen anywhere a shift like this? It's like what's the word? Well, we may have seen it in let's say maybe you're driving and there's if there's a mountain is cut. Okay, and if it is made of, if there's a history there, and there are big movements of the, maybe the whole continent has moved, so, and it moves like this. So it used to be like this, and then it's been shifted in the horizontal direction, and which may produce this kind of a skewing effect. So once again, so this is what we're applying for to do in dimension 2. All of these operations have to be combined into a uniform picture. But before that, distances. Okay, so we are developing a uniform um, attitude and the formula for all spaces of all dimensions. So on the line, that's how we do it. Once again, let's do the easy problem the hard way. Okay, so how do we measure distance how do we compute the distance between two locations if we know their coordinates? And the answer is we subtract. Okay, so, and then what? The P and Q, distance between P and Q is known. One is located coordinate 4, the other one coordinate 6. What do we do? You see the point, there's the point there. So if we go from P to Q, then we subtract 6 minus 4 is equal to 2, which is fine. But if we were going the opposite direction, then it would be 4 minus 6, which is negative 2. But the distance is 2. So what is that? What do we use here in order to
Absolute value.
absolute value, right? So because distance is the same, going from P to Q, Q to P, the answer should be the same. So the answer is just to use the absolute value and say that's the notation that I'm introducing, which is going to go on for the rest of the course. dpq, the distance, and in this case, it's in the dimension 1. And once again, there are seemingly 3 different cases, which to the left or the right, that's not going to work long term. So depending on which way, how they located, subtract one from the other or the other from the first. So instead, just subtract and do the absolute value. Okay, that's literally one of the best reasons for the absolute value function to exist in the first place. So that the distance is, once again, the direction doesn't matter, and that's, you may have seen this in calculus, that the direction you go from there and there, you're computing the velocity, and it matters which way you're going. Distance does not. So distance is not the same. I guess that's as a warning. Distance in this context is not the same as displacement. Yeah, it is interchangeable frequently in the everyday language. But if you do in calculus, for example, it is displacement. You divide by time, and that's how you get velocity. Okay, so it matters, and the sign matters because it points out the direction of motion. And here it does not. So we want to have the same number. Okay, so the distance formula is simply the absolute value, dxx prime. Xx prime, on one hand, they are points, but also they are the coordinates of those points, and therefore, if the coordinates, they are numbers, we can subtract them. Subtract, no matter which one comes first, second, take the absolute value, that's the distance. Okay, so once again, easy problem done the hard way. Why so? Because we in dimension 2, we want, let's skip this, but in dimension 2, we want to have a similar function. Once again, the direction doesn't matter, except there are not 2 directions, there are infinite many directions, and so that makes things slightly more complicated. The absolute value of m, if we have a transformation, turns out to be the what just came up a minute ago. So the slope of a linear function has a different interpretation now. It is the stretching factor. The absolute value of the slope, if we abandon the idea of x and y being coordinates to each other, so this is slope m, or I do the same function. I put x here, I put y there, and then if this is the distance was 1, and this becomes absolute value of m. Okay, so m could be negative or positive, right? But if we were to speak of stretching of our x-axis, then that's by that factor, it is being stretched. Once again, the direction doesn't matter. The distance formula for dimension 1. Okay, so as you can see, what happens is if we are what happens to the distances in horizontal and vertical directions, are changed proportionally. But if you have a diagonal direction, then the only way to find out is the Pythagorean theorem. Okay, so for dimension 2, if we want to measure distances, even though and that's the big point that I'm trying to make is that these are known. Okay, so what we just discussed, in dimension 2, the axes are the one-dimensional spaces that we know how to handle. Okay, so we know if we stay within horizontal and vertical, we are set. So that's the picture on the left. we accept. So that's fine. It is the diagonal direction that require a separate study, and that's why we need the Pythagorean. Okay, I'll stop here. Okay, so